Okay, so let's start. So I think we're gonna make some connection between the lazy random walk matrix and the power method for computing a second eigenvalue of Laplacian matrix. And here, this is just to recall that the matrix that we really just compute in the power method is just this lazy random walk matrix and compute it to some power. So why is that? Well, you just need to recall the power method, right? And then where is it? Then we see that oh no, yeah, right. So we see that when you compute okay, maybe so the matrix, when you want to compute the second eigenvalue of Laplacian, the matrix that you look at is this matrix M, right? Which is defined to be this, like I plus the normalized adjacency matrix. So, okay, well, this is not exactly, this thing is not exactly W tilde, but they are the same if the graph is regular. So that is if the graph is regular, then so if G is D regular, say, then you can see that this is just A over D. And A over D here is also a walk matrix if the graph is D regular. So and this is nothing but 2 W tilde. So this is just like to make connection that you can actually view the power method as some like some step of doing lazy random walk if the graph is D regular. Okay. And so let me recall the thing I talked about yesterday. One is local min cut, and one is isolating cut. Can you like remind yourself or tell me roughly what is the goal for both of them? Yeah. Can you tell me anything?
In a big graph, if there is a small small cluster of vertices which can be separated from the rest of the graph by small cut, then we should be able to find it using order of k square.
Right.
Where k is the cut that is small.
Right. Yeah. So that is like the goal of local min cut. Yeah. How about isolating cut? What is the input and output? Yeah.
There is a set of terminals that we want to
right? And we want to do it for every terminal, yeah, right? So like the output of isolating cut is just not one cut, but it's like a T, like terminal many cuts, yeah, right? And I think I'm gonna actually, I should talk about like, so I talk about what is it and how it works, but I kind of skip the application. But maybe I should talk about this application in class, so that I'm not sure. What do you think? Should I talk about it today or in class? Because today is just exercise.
In the terminal isolated mid-cuts, so if T is not power of 2, then we are separating it into many blocks, which are like empty blocks.
Oh, so if it doesn't matter if T, like the size of T is a power of 2 or not. For example, like we really just that for each of the iteration I, we just separate the terminal set into two sides, right? A red side and blue side, and the one that have ith bit to be the one whose ith bit is 0 is red and otherwise is blue, and you can like make this partition regardless of the number of terminals, right? Yeah, like if there are like 3 terminals, you can still like it's enough, like 2 cut is enough, 2 iteration is enough to like separate, to isolate all of them, but it doesn't need to be like the number of terminals need not to be a power of 2. Yeah. Okay. Okay. And I kind of skip this proof in class, but the idea is it's really like I don't have a better proof than just this case analysis, really. So if anyone knows better proof, can tell me. And the way that I prove is just that I just draw 2 sets A and B here that they can intersect, and then just draw all the cases that of the cut edges, where can it be? This is an edge from A minus B to outside everything, and this is an edge from A minus B to intersection, and so on. So this is like all the cases, and then I just summing up over all cases here. Like for example, all the cut size of A is just this guy for A, and from here F, and this should be C, and from here to here, and then E here, right? And I just do this and compare them, and then it will turns out that like all the terms, like, and then compare all the term here, and then it will turns out that this is at least, like this part is at least another side here. And the reason is just that if you look at whenever A appears here, A appears here too. When D is here, D is here too. So every term, and if C here appears 2 times, it appears 2 times here too, and so on. The exception is just E. E can appear only on this side. Yeah.
If we like the other definition of submodularity, then maybe it's immediate. Like, I don't know, like if you have like two subsets, like A is subset of B,
Yes.
and now like to the larger subset, if you add some vertices, like compared to the smaller subset, the cut size can only increase by smaller because that vertices can have edges only two.
I see. Yeah. Yeah, that's true. That's like good for intuition. Yeah. So what Aditya is saying is that there is another way to state, like equivalent way to state submodular function, which is here. So if maybe write it like this: if S is a subset of S prime, then if you look at a function here, S union some element E, this is going to be at least
Change is minus f of s.
Oh yeah, thanks. Very good. Thank you. Right. And this is called like this is basically equivalent to this. But this one have a better way to like interpret it, I think. Yeah. That is like a diminishing return. So it's thing like if you have some small set S and you add some new element into it, then the increase in function, the increase in value of the function is here, right? And now you look at the same increase for S prime, but S prime is a superset of S. Now we say that, okay, the increase in your value is actually diminishing when like the increase in value from of S prime is at most the increase in value of S, because you are kind of too big already. But yeah, this is the interpretation. And now, right. And now I guess it's easier to verify this, that this is the case for cut. Maybe I write it like this. Because if this is S and this is S prime, and how would you verify this again, actually?
You take S union V as A and S prime as B.
Like when we add some vertex V to S, V is outside both of them.
Yeah. So
Yeah, S prime as A.
if this is V,
Yeah, so whatever exists, like V has the outside, like outside both S and S prime, they're anyway there. So when V is transferred to S, like the decrease would be like the number of neighbors of V.
right.
V is transferred to S prime, yeah, it has only more neighbors.
Right. Yeah. So the cut size, how much the cut size increase from S here So it increased by like this much, but it also decreased by this much. But for S prime, you will decrease by this much too. So like this green thing actually decrease for S prime, but it increase for S. Yeah. Good. Anyway, yeah. Yeah, I think this might be a bit easier to think about, yeah. And can you tell me why this doesn't work for directed graph?
I have one more doubt. In
Yeah.
directed graphs, how do you define a cut? So is it S2 V minus S or it's both ways you add?
It depends on your definition, but usually we define it to be the number of edges going out of a cut.
Out of S.
Yeah.
Okay. So the ones coming from V minus S into S, we don't consider them as the cut.
Yeah, usually.
Okay.
But it depends on how you define it. But today or in class, I will talk about number of edges going out. Yeah. So can you give me just simple example when this actually goes wrong, where this thing is like the number of edges going out? Any suggestion? So maybe let me try. So maybe how about this kind of graph? Okay. I'm just trying right now too. So let's see. Well, suppose A is here and B is here. And let's say that I'm directing edges like this. And here. Does it work here? So cut of A is 1. No.
If like all those red edges were like to B, all the red edges are like outgoing and all the green edges are like coming to S prime.
Can you come to draw maybe? Or
I haven't found like a concrete example.
okay, we are doing it online right now, so yeah.
Like I'm saying, if those red edges were all like coming from V to S,
Oh,
or,
okay. Coming from V to S.
or okay, what is this other way? Like red and green edges should be like, the pink and green edges should be like opposite direction. Then it would actually work.
Mm. Okay, let me just.
All the edges from S to B, the pink edges should all be directed towards V.
Okay, everything direct to V.
And green edges like away from V. All away.
The red edges away from V.
The green one.
The green away from V. Mm-hmm.
Now this should work, right? I think. Like when you move V to S, the cut size like drops by the pink amount.
Yeah. When you move V to S, then the cut size drop.
But it increases by the green amount. So let's say pink are more.
Pink and green are independent, so we can like it need not satisfy this any inequality or
Yeah, so green, if the green number is more,
Mm-hmm.
that would be good. Right? Because when you move V to S, the cut size is increasing by, is dropping by pink, and it increases by green.
Mm-hmm.
So if green is like lesser than pink, then the net cut size drops this. Like the net cut size drops, except for the red edges, there is a drop in cut size.
Mm-hmm. Mm-hmm.
But now if you move V to S prime, there is no change in cut size in the green and pink edges.
I see. I see. I see. So, yeah.
but that is what we anyway want. So it's the other way. Green should be more and pink should be less.
This is like pink should be a lot, right? Because if pink is a lot, then when you add V, then the change in the cut size actually
Is less than red.
decrease. This is now negative, like something negative.
It's negative plus red.
Yeah, plus red. Yeah, plus red.
And then it is 0 plus red.
And here is 0 plus red. Right. So let's try to make it like in such a way that it is super simple.
Just like choose one vertex for each edge.
Right. So maybe V is here, and then this is just a node S, and this is this is S prime, and maybe A and B here, and then there is really a lot of edges here. Okay. And then there is also right. I just want to get this A and B. How should I define A and B here, actually? So if I what if A is in B? Okay, but okay, this might not be too interesting.
A intersection, you have to put lot of edges out of A intersection.
Okay.
Towards A.
Yeah, if A is in B, I think. I mean, if we can ensure A and B, then.
Yeah, so you can put lot of edges out of A intersection B to A.
I'm not sure what you mean. Do you mean A and B here?
Yeah, two sets A and B. And from A intersection B, you can put lot of edges towards A.
Okay.
Those are the pink edges we are talking about.
Mm-hmm.
And yeah, whatever the green edges are from A to B, A minus B to B minus C.
Okay. Yeah, but this is small. It can be 0.
Yeah,
Yeah.
it can be 0.
Yeah.
So then we are increasing delta of A intersection B by what?
So the cut size of this is really just this pink, but now I'm confused because the cut size of this plus this is also this thing, the same.
No, we have stuff from A minus B to B minus C.
But okay.
Oh, that's anyway great.
I'm sorry. I should prepare this. I didn't think that it would be hard.
I mean, it's just little messy, maybe not hard.
Yeah. Can you say again the suggestion? From B to A intersect B.
Because we're coming out.
All right, I go and think about it again. Sorry about this. Hi.
I mean, since those definitions are equivalent, we know that we have an example.
Yeah. Okay. And okay. So also in class, I kind of go through this part of the algorithm quite quickly. That is, so recall that I talk about the finding short path in square root n time on expander. And I say that if you do just like square root n random walk from S and square root n random walk from T, and do it long enough such that the random walk mix. So you go to like you really basically go according to the distribution of the degree. So it's random, like each node is kind of random proportion to the distribution of the degree. And then we say that if the set from S and the set from T is big enough, like square root n, then they're gonna be intersecting. and I just said that it's by birthday paradox. Do you need more? Need me to tell you? Like, do you feel like you need more details on this, so that we? So this is fine. Yeah. All right. Good. Okay. So then, actually, I'm not sure. Is there anything else you would like to ask, or we should think about? Otherwise, I should just come back to talk about open problem again, I guess. So by the way, I actually think that this really can be done. So, and maybe the time is actually better, PR. So, So I will just try to sketch the idea, and if anyone wants to think about this one, it might be kind of relatively more approachable than other problem, I think. Yeah. So, and anyway, it's good to know some background knowledge related to this. Okay. Let's see. So first thing is that there is a really nice claim about the number of mean cut in the graph, actually. So suppose that you look at a graph, not hypergraph, just a graph, okay? In a graph G, we have that the number of alpha approximate mean cut in G is something like at most 2 times n to the, it's like polynomial in n. Yeah. And this is like a very nice result by Karger. Yeah. And once you know this, then actually it implies that if the mean cut is lambda and if you let G P to be obtained from G. Oh. by sampling each edge with probability P. And if then we have that, so maybe let P be something like O of log n lambda, then GP, like min cut of GP is basically min cut of G times P. So what I'm saying here is just that if you look at GP is nothing but when you have a graph, you just sample each edge with probability P is a subgraph of G, right? And then if you look at any cut, the cut size of S, the cut size of like crossing S in GP, in expectation would just be like a cut size in G times P. So this is just in expectation is trivial. But now, like, can we say that actually the cut size really concentrate around its expectation? And normally it would if your expectation is at least log n, right? Because when your expectation is at least log n and the random variable is from like independently sampling things, then you can use Chernoff bound. However, like this is the case when there are like when I say that I can use Chernoff bound and I need the expectation to be log n, and things would hold with high probability. When we say that with high probability, it means that with probability 1 minus 1 over poly n. So this trick would work only if we are talking about when there are like just poly number of things that we are look at, and here it works because we really say that there are just poly number of things that we are looking at, because the number of min cut, they are just poly number of min cuts. This is why you can use Chernoff union bound and say that every min cut actually every cut actually we can say that not just min cut, but every cut would concentrate it around its expectation. Yeah. Okay.
Is it not optional square?
Sorry?
Is it not optional square?
Yeah, epsilon square. Yeah. Okay. So that was just something super quick, but I'm mentioning here because we can try to do something like this for hypergraph too. And if a hypergraph, so if you have hypergraph H and each edge, now an edge is an edge has not just 2 endpoints, but can have up to R endpoint. We call it rank. Then you can talk about like HP and say that and if you choose P to be like good enough, then then you can specify hypergraph so that the min cut is kind of preserved too. And what should that be? I think it should be just here. You just set P to be R times log n over lambda square. Right. Yeah. So what is good about this? Well, the thing is that in class actually on Tuesday, I'm gonna tell you. So here you can see that the min cut in GP is around actually log n, right? Because you multiply this thing by p. So the min cut in GP is small. And the min cut in HP is going to be something like log n times r. Think of r as not too big to small. So the point is that you get some, given any graph or hypergraph, you can make it in such a way that the cut size now, the min cut size is now small. And in class on Tuesday, I'm gonna show that there is an algorithm that is fast. Like you can use it to find min cut fast when the min cut is small. And which is why things can be combined, and at the end, you should be able to get something like PR algorithm. So this would already beat the best known algorithm of PN. But this one is exact. Yeah. But if you want just approximation, then I think PR is going to be very approachable just from material in class. Oh, okay. I'm ready to talk about this one too. Have I talked about this before? No, right? Yeah. Okay. So I mentioned in class as well that hypercube is an expander. But hypercube is a very, very nice expander, not just some expander. So like complete graph, a clique is a nice expander, but it's dense. But expander somehow, an arbitrary expander is good too because it's well connected and everything. But for hypercube, it's kind of sparse. It's very sparse actually. Like it has only n log n edges in the graph, but it is very well structured too. So let me tell you one example why it is good. So if you have a hypercube like this, one thing which is very nice is that suppose that I'm giving you two nodes. A and B here, then it's very easy to tell where is the shortest path from A to B. Because each node in hypercube, you can describe it as some bit string, right? Let's say this is 0, 0, 0, and 1, 1, 1. And what you need to do is just keep flipping the bit. So which means that you go, by flipping the bit, it means going to some direction. And you just need to keep flipping the bit in the right direction. And you know that you can just given 2 nodes, you can really you know what is the shortest path. It's very easy to compute shortest path. And this is not I taught in class that, okay, given any expander, you can compute short path between 2 nodes in square root n time. And that is for arbitrary expander. But in hypercube, it's just super easy, right? You can get it in constant or log n time, something like that. So it's a nice structure. Now, this question asks, given an expander, given any expander, given an expander G, we know from class that, and let's say it's a uniform degree expander with, actually let's say with a degree log n. Yeah. So everyone has degree log n. Yeah. Then we know from class that you can embed hypercube into G, right? Because H, hypercube, this is hypercube. Because H is log n restricted demand, so you can embed H into G. And you can do it in polynomial time for sure, because this is multi-commodity flow problem. The question is just that, can you do it in linear time, in nonlinear time? And the best known algorithm right now is not nonlinear. It's close to linear, but not quite nonlinear yet. And if one can do it, then basically it has a lot of application in psi theory, but you can think of it as kind of imposing structure into any arbitrary expander. Given an expander, once you can embed a hypercube into it, then it means that you can immediately route. So, okay. So suppose that I can embed with small congestion, and maybe you can ask for this too. That is, in each of the path that you embed is a short path. All right, you can ask small dilation. By dilation, I mean each path in the embedding is short. So if you can do this, it means what? It means that if I now given any 2 nodes in expander, instead of spending square root n time to find a short path between them, now actually it's going to be much better. Why? Because I just look at corresponding S and T in the hypercube and look at, let's say I choose this path in hypercube. Each of the edge here will correspond to some short path in the graph because the embedding is short. So this is like short path here. Let's say from U here, U, and V here, and here. So it means that now I can route in expander in just polylog time. So like, it's very nice. Dilation, yeah. So just to say again, yeah. Dilation of embedding